a bit exhausted, but we're going to go ahead and implement some of the things that Dan told us in the lecture before for the lunch. And we're going to try out quantization, feel it with your own hands. Please go ahead, follow the link I shared on Slack. And when you open the notebook, just click open in color. And I will do the same, and I will be doing the exercises as a notebook in the same tempo of you, not the same, but I will be typing the solutions myself as we go along. So is the font size okay for you guys, or should I increase it? Can you read comfortably what's written on the slide or not? Okay. How about now? More? Okay. More or bigger? Anyone? Okay. Sorry? Yeah. Is that okay? Okay, great. You can go ahead and start first couple cells, because it will take some time to download packages and import everything. So you can just go ahead and start the first two cells. And I'm gonna give a quick overview of what's gonna happen. So first of all, we will talk a bit about low precision formats. So what exactly are these quantization formats that enable us to get so computer efficient, right? We're going to look at the values. We're going to look at int and floating point. Then we're going to do some basic quantization ourselves. We're going to quantize the metrics, dequantize it, see how that transform goes. Then we're going to take a small LLM already pre-trained. We're going to quantize it layer by layer and see what works or maybe what doesn't work. And then the main goal of this tutorial is to implement GPTQ algorithm. And if we achieve that, I think we did a really good job, and we're done. And the very last section, QA with distillation, is like an extra task if anyone is bored and already know everything, that they can go ahead to the very last. Okay, let me see it. Oh, it just started downloading all the packages. It will take a couple minutes, so yeah, I encourage you all to start and yeah, this tutorial can be run on GPU if you're lucky and Google Colabs give you some, but if not, it's also absolutely fine to run on CPU. As it is my case, it is running on CPUs. And while it's all importing and downloading, let's talk about quantization formats themselves. So, but okay, what low precision formats do you know? Anyone knows? What formats are there? Like how many precision do you usually use? Like in your regular computation, in your like usual language model? 16-bit, yes, exactly. That's what we called half precision, because originally it was 32, and then people noticed, oh, we can actually go to 16 without losing much, without losing anything actually. And later people thought, okay, let's go lower and lower and lower and see where it breaks. And as we'll know, there are integer formats and floating point formats, and both of this type of formats has been adapted to low precision weights. So here, on the slide, you can see just a quick reminder of how an integer value is encoded in memory, how a string of bits, well, it's literally a binary representation of a value. And we're gonna implement and see all the values a bit later. And also we have floating point formats, which are a bit more complex. So just a quick reminder, I'm sure you all know that, but we have one bit which decodes the sign. We have the next several bits which decode the mantissa, and then we also several bits for exponenta. And so what it does is allows you non-uniform spacing between the values that it represents. And so exponents control the range, so the powers of 2 that are available to you, and mantissa controls the numerical precision of a number. And just so you would have just an image for you to look at. So these are floating point formats. So FP16 and BF16, yes, the have precision formats as we have here. And we go as low as there is FP8 formed. And do you know what's the lowest floating point format that has was officially documented by IEEE? That would be FP4. So just 4 bits per parameter. And in the next exercise, we're gonna see which values can we actually encode. So we are going to the task 0, very first one. So I would like to ask you to implement int4 and floating point 4 values as decoding from bit strings. So you can see 2 functions here in the cell. And the first one is for int4, the second of FP4. And you can look up at the definitions above. They should be more than enough to decode bit values to the values that are represented. I would give you a couple times to do that. Please, if you have questions, ask me right ahead. Okay, I think it's a fairly quick and easy exercise. I'm gonna start implementing it just here. And so what do we have here? First, we have signed integer. So the first bit is going to be the first bit is encoded so-called offset to represent values both negative and positive. Offset is implemented, so which looks like this. I'm not making it up. You can go, let's scroll a bit higher up and see the formula yourself. So I'm implementing actually this one. And so I've done offset, and then it's just regular, just converting binary number to tender. Let's go. We gotta skip the first bit because it's offset. Right, how's it going with the integer 4? Have you finished? Does yours look similar to mine? Maybe mine is wrong, I don't know, we'll see. Hmm? Sorry, a bit louder, could you? Sorry, in the first slide. Yeah, thank you for the question. Yeah, here I've just had constant bits equal to 4. Yeah, but I mean, we are going to work with like before numbers. Feel free to hardcode it to 4. It's okay. How's it going with int? Do you agree with my solution? Is it wrong? I can make mistakes, absolutely. Then we can move to floating point numbers. And here's a bit of a trick because for the floating point numbers, when exponenta is exactly 0, we call it subnormal range. And the number representation differs a bit. So we could be able to represent values from 0 to 1, but it's already implemented for you. And what you're asked to implement for the floating points is the normal range when exponent is not equal to 0. And you asked to implement the floating point number representation yourself. Any questions so far? Floating points? Anything unclear about them? All right, I guess not. Then I will go and implement floating for myself. So here bits are already converted for you. So we have sign converted from sign bit. We have already exponent converted from binary to floating point, and we have mantissa. Also, it's just 1 bit for FP4. So we're going to have something. The first, we're going to use the sign bit. So we're going to sign multiply it by, now we're going to have 1 plus mantissa over 2. So that is exactly this binary representation, which is denoted as 0.m. This is just a binary representation that we are converting to decimal. And we are also missing the exponent part. So I'm going to go ahead and have the power of 2 here, and which going to be exponent value, which already converted for us. minus the exponent bias. Okay. Does it seem correct? Any objections? Okay, let me start the cell, and once you're finished implementing your 4-bit format, just please run the cell, the next one, and you're gonna have a cute visualization like this, showing you all possible values of integer format and FP4 format. And mine seems to be correct, I think. If you get similar one, then your implementation is correct too. Okay, cool. Why do you think I show you both integer and floating point? Right? Can you guess which one is the better? Why don't we just choose one and just stick to one for quantization? Just one of them. Any guesses? Sorry? Yes, exactly. Well, they both use 4 bits for memory, right? Operations with integer values are a bit faster. That depends on your hardware. But then floating point. But then why don't we ditch floating point? Why don't we do everything integer if it's faster? Why keep floating point? Sorry, you said more precision? Less precision, but I mean, they both store 4 bits, so that's totally, in total 16 possible values. Why keep floating point? Anyone? Yes, go ahead. Okay. Any more answers? You? Yes, exactly. Well, where it comes from is this: if we look at model weights distribution, they are not uniform at all. They usually look like Gaussian or something Gaussian-like, with peak at 0. And so we have more, like the majority of values in the weights of a model are really small and close to 0. So it makes more sense to allocate more precision to those tiny values close to 0 and less precision towards the tails of a distribution. If you remember, the analyst had a nice plot with, I think, real values distribution exactly like this. So it's more dense near 0 and less dense with the tails. Okay, but quantizing values to FP4 values is a bit more tricky to int. So here in this tutorial, we're going to continue with quantizing to integer values, just because it's a good first practice to deal with int. They're so nice, evenly spaced, and so on. And yeah, sure, go ahead. Yes, I could, but I guess the teaching assistant also could help you with that. Is it good? I want to go ahead. Or your neighbor maybe can help you with this? Have you? Teaching assistant? Can someone help? Thank you very much. And we'd like to continue. So, all right, we have integer, floating points, and for now, for today, we stick with integer values because it is for you, for me, and for. All right, we have some equal representations for integer 4. Now we're gonna somehow transform our values of our matrices of a model, which can be like whatever, right? represented in 16 bits to this 4-bit format. And the question is, how do we do that, right? Because sometimes values are really large. They can be on orders of magnitude of thousands. Sometimes they're really small. And if we just do naive, like rounding to closest integer, we would lose, like the error is going to be huge. We would lose a lot. So what we're going to do is we're going to do this like linear transformation of our input. If you look at the formula, so we're gonna, in here, denotes our weights in full precision. We're gonna scale it by some scale in and add an offset, which is called 0 here. And we're gonna do it for a set of weights at the same time. So if we have several weights with large magnitude, the scale is going to be large. And if they are, for example, far away from 0, the actual 0, then the offset 0 going to be some large positive number. And turns out this scheme is already good enough. I mean, works quite good. This is just linear transformation. And throughout this tutorial, we're going to use unsigned integer 4 just for convenience. So our output values, quantized values, going to be from 0 to 15, which would be 2 to the 4th minus 1, right? And the first exercise for you would be to implement this actual transformation, which we call quantization procedure or quantization function or quantizer as is. So you're going to have to map the input values to the to integer values from 0 to 15. But before we do that, let's discuss why it may be reasonable to quantize weights in sets. Why would we want to do that? Why don't we choose the whole matrix and choose one scale for everything and one offset for everything? Sorry, could you be a bit louder? Yeah, you're a bit ahead. Just if you're given a matrix and you're asked to please go quantize the matrix, how would you do that? Like, how would you select the sets to allocate the scales and offsets to? Any more ideas? Questions? Sorry? Could you speak up, please? Yes, exactly. That's really good answer. So we're gonna have to look at what function this matrix is actually like performing, like why is it there? So here we're gonna talk about weight quantization, and weight for linear layers are usually represented as a matrix, exactly. And activations flow through the linear layer. This is input tensor, which is here denoted as X, gets multiplied by matrix W, which is the weight, and the output activations are produced. And this is your, okay, offset B also, okay. And this is your classic linear layer. Yeah, a favorite linear algebra, I think. And in this notation, because you have you could have everything transposed, but let's forget about that. In this notation, to produce each output, you need to take a row of W, right, and a column of X. That's just how matrix multiplication happens. And turns out it is quite a good idea to quantize the values in your matrix row-wise, because once again, this matrix matrix, the size of output features is its height, and input features is its length. And some output features might use I don't know, large values on average, output channels that are more sensitive or more, I don't know, carry more information or whatever, call it as you wish. And others might be, I don't know, not so large in magnitude. And so that's turned out a pretty good approach. But could you tell me, why don't we go further and select smaller and smaller blocks? Why don't we also divide each row into more sets and quantize within each? Why don't we go just like super low? Any ideas? Yeah, please go ahead. Yes, exactly. We are, of course, representing each quantized values in 4 bits. That's really great, 4 bits per parameter, very efficient, but we also have to save the scale and the offset values, which would be in full precision. And then for every quantization like set block that we choose to, we have to say 1 scale for each and 1 offset 0 for each. And so the more this quantization blocks you would like to have, the more extra memory you would have to spend to store all these values. But of course, you can go smaller, and it's, as usual, a trade-off. But in this tutorial, we're going to go row-wise. So if you have already looked at the next exercise, is to implement this linear transformation with first to produce this scale and 0 offset for a matrix that you're given. So here we're doing quantization row by row, so each row is quantized independently. And how do we choose the scale and 0? Any guesses? So imagine we have our input vector with full precision weights. It has some weight distribution, like some minimal x value, some maximal x value. How do we choose scale and offset then? Yeah, we could do that. But here, remember where we are mapping to? Our final values are unsigned integers, so values from 0 to 15, so 0, 1, 2, 3, 4, and so on to 15. And it is just a linear transform. And we want to kind of preserve, as we can, distances between values in x. So we want to have, we don't want to any values in x like to collapse in one point. So where would you map the smallest element in the vector x? Yes, exactly. That's correct. Where would you map the largest one? Very hard question. Yes, the 15, exactly. And what about all the rest? Yeah, exactly. And in between, exactly uniformly, because it's just a simple linear transform and just a simple linear map, and they're gonna be uniformly spaced in this transform. All right, so you can go ahead and implement scale and 0. Oops. I'm gonna go ahead and slowly also do it myself. By the way, do you think it's the optimal mapping that we're doing? The just linear transform to interval from 0 to 15? Is it? Why? Yes, exactly. It's exactly the point why floating point are better for weight representation than integer, because integers equally spaced, and model weights usually don't follow that pattern. They are somewhat like Gaussians. They need more precision near 0. But for now, we are perfectly fine with this equal spacing that we have. Any more questions about this linear transform we're doing to quantize our values? Okay. Let me go ahead and also implement it. It's gonna be something like notice that there the maximum available value of like quantized representation is function parameter max abs. So here you can see it defaults to 15, so 15 is maximum value for integer 4. So we're gonna use that. Well, okay, and once you have some working version of your scale in 0, you can go ahead and also run the next cell, which will show you where the values of this example vector tensor are mapped to. So I apparently was correct, and I mapped my tensor, which has values from -1.2 blah 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 to 1.8. I mapped it correctly to values from 0 to 15, which is exactly what we are going for. Okay, and when you think you're good with your scale in 0 implementations, you can go ahead to run the next cell, and it's going to be some tests. Oh, my scale is the wrong shape. Okay, I need to go and fix that. Because output should be shape. Yeah, and if you implement everything correctly, then you're gonna get one more assertion error, because there is one extra condition that is just for convenience, that if all the values in a row are identical, let's set the scale to 1. Mm. that work? Yeah. Okay, I think I managed to do something. Are there any questions? What happened here? Why did I write those symbols? How do we do that? Why? I mean, when you're doing it for the first time, yeah, it will take you some time. Just think of it as an equation, a system of equations that you're solving. So with just a linear transform, right? So we have one parameter scale, one parameter 0, and we have two equations, right? In our system. So first we are mapping minimum value to 0, and we're mapping maximum value to 15. And that's all you need. You have two equations, two variables, you solve for them. And if you substitute this scale and 0 values back to this transform, you can check that you're going to get exactly what's needed. So 0 and 15. Any objections to that? Or questions or thoughts or anything? Yeah. Yeah, why you're asking why the minus here? Yeah, so I was looking at this equation. It's just a bit above in the comment. So what I was solving for, I can just write exactly the equation that we're solving for. So I want to have x min, like minimum value, over scale plus 0. I wanted this to be equal to actual 0, right? And to solve for this, I'll just getting 0 is minus x min over scale. Yeah, and if I have the scale already, well, yeah, that's exactly how I got. Yeah, so, let me write down also another equation. So it's just x max, maximum value over scale plus 0 would be exactly maximum absolute value, which is 15 in our case. So these are two equations that I solved, and I got my two variables. Any objections to that, or questions, or comments, or whatever? Yeah, sure, go ahead. Yeah, I mean, it's just an extra, like for convenience, imagine if all the values in your row are exactly the same. So then you have scale equal to 0, right? Because maximum value minus minimal, it's 0. And then in our transform later, we're going to divide by scale. And that's not nice to divide by 0. So we say, okay, let's have an agreement. If it's zeros, we're just putting 1, right? So we're just setting scale to 1, just not to divide by 0. That's our convention. Well, our values have to be in unsigned integer range, right? So from 0 to 15, and last, yeah, this one, or this one. It's just asserting that your output values, your produced values, are in the correct interval, right? So it's just exactly the transform. x over scale plus 0, it should be above or equal to 0, and it is just a small negative constant here, and it should be below 15, right? And it's just like small numerical constant to ensure that we include 15 exactly. All right. So no more questions. Then, okay, we have our quantization function. They're going to map our values to unsigned integer values. And let's actually do the quantization. So we're going to use this scale in 0 that we just learned to obtain and implement our quantize and dequantize functions. So to be able to transform our values from full precision to low precision. So there is already a hint for you that you should use torch clamp. And since the output values are all integers, then you should probably use the rounding function. Yeah, so these are helper functions that we will use later. Any ideas why we have dequantize function here? Why don't we have just quantize and that's it? Yeah, go ahead.
I guess, suppose the biggest bottleneck that we have is the memory. We try
Okay.
to moving the best letter. So we will copy quantized memory or actual operations once it's already.
That's a nice guess, but not exactly. Actually, on GPU, what we would like to do is do low precision arithmetics. That's what GPUs are good for. And we need dequantization function to be able to map back to the actual values, right? Because we just, if you look a bit above, so this example tensor that I mapped to values from 0 to 15, right? If you have this tensor, like you have no idea what the original values were, right? And to be able to propagate input to network, you would actually need both these quantized values and their scales and zeros, and to map them back to the floating point range, but with some error. Yeah, so if you notice, like this quantization like transform that we've just built so far, it actually mapped one value to 2.5. And it is not an integer value, right? It's half. So that is something that we should implement as in the next quantize function and make sure all the values are actually integers, right? So we have some transform, but it could also produce some non-integer numbers, and we need to ensure all integers. Okay. Yeah, this one's really fast, so I will just go ahead and implement this. So I have my input x. I will do my transform, x over scale plus 0. All right, then I need to lump it, just to contain it with an interval from 0 to maximum possible value. And then still the output of this operation might be non-integer values. So here I'm going to enforce integer values by doing the rounding operation. It's just classic round to nearest integer value. Oh, I did write it wrong way. It should be clump like this. Then gonna have my dequantization function, which would just be exactly the inverse of transform we just did. And it's a linear transform. So the inverse exists. And so I should take my quantized x. I should subtract 0 because we were adding it before. And I should multiply it by scalar, I think. And that would exactly map us back to the values we started from. And then the very last helper function, it just for convenience. Yes, and it's also in bits. I'm gonna have the bits here. Okay, after you implement those three functions, you can go ahead and look what your quantization transform does to your vector. So we have some random vector with 6 numbers. We're gonna produce our scale 0, quantize it, look at quantized values. Now they are all exactly integers, no 0.5 values, no half integers, all int. And then we're gonna dequantize it back to values. And as you can see, we lost a bit of precision, right? So when we applied quantization procedure and then the inverse one, we lost. So minus 0.7, for example, the second element, it got transferred to minus 0.8. And that's the quantization error that we have to live with, which is inevitable when you try to use less bits for representing your numbers. Yep. And then you're gonna go ahead and I miss bits here. Oh, and I don't need to return them, I think. Okay. Right, congratulations, we built our true quantization function and dequantization function. And now how about we go ahead and try it out in a real language model? So here, we're gonna go ahead and look at a 50 million model, open source. So you can all download the base, and there are some helper functions that you need to run this cell. And then, okay, we have our model and it has some different layers, some different functional layer, and we're gonna replace some layers with quantized ones. Any ideas how should we do that? Like large language models, they contain various blocks in the architecture, right? We have embeddings, we have attention layers, we have MLPs, right? We have some maybe gates, maybe something else. How would you do that? Where in the model would you apply quantization to? Sorry? You're saying after training? Yes, yes, that's exactly what we're doing. But to which model components would you do that? Like we have different operations, right? We have softmax in attention, or we have just linear function, linear layers, or we can have. You can just guess. You can just like, okay, on all layers or on some, or how would you do that? Yeah, all right, all right. We're gonna end this game. Oh, you have an answer? Or? Yeah, yeah. Like the matrix multiplication is the correct part here because notice before this thing we were implementing is quantization row by row. So we can efficiently multiply our weight matrix by the input activations, right? And this was all so that we can now replace linear layers in our network, all of them actually, we're not skipping any, with quantized layers. They're gonna store quantized values. Does that sound okay? I mean, it's a bit, I guess, more complex topic, but when you're trying to quantize something which is not a linear layer, which is not a plain matrix multiplication, you're going to have problems. Like it's a lot more difficult task if you're trying to apply it to attention or I don't know, some weird architecture, some RNN stuff that requires a bit more machinery than we're doing right now. But we are so 1 second. This should be yeah. So here in the cell, you're asked to implement just this substitution. So to replace all true linear layers with our new quantized linear layers. So there is a little helper for you already that you should create new submodel. Right, so I'm gonna go ahead. I'm gonna use a function from before, or helper, little helper function, measure and quantize. And I would use it. I would say it would get me X, like weight quantized. It's also gonna give me scale and 0. And I'm gonna use this function on my weight matrix. So for the linear layer, I'm looking for the weight, and I'm gonna for the tensor. And so if you use a quantized linear class constructor, so what it asks for quantized weight, scale, 0, and bias. Bias is just a visual bias the one linear layer has. So we just propagate, it just is left as is. So I'm creating a new quantized layer with, why are you not happy? This, and it also asks for this. Okay, once I've created this new submodule, I'm gonna go ahead and use the helper function in the cell above, which is called straight replace submodule. Very easy. And so it takes as an input row. And my new submodule. Once you've done that, you can go ahead, download the model and the tokenizer. And let's test out our model. Oh, I missed one argument. Measure in quantize also requires bits. Okay. Oh yeah, I think I just call it like this. It could take you maybe a couple of minutes to download the model. Yeah, it's all right. Yeah, the Wi-Fi speed is not great for me, as you can see, but it's going. Yeah, it's really slow. So let me just scroll a bit ahead and look at what's next. So congrats. Actually, if you completed this one successfully, then you have your own large language models, which you quantized, which for all linear layers, you replace full precision values with low precision. Bye. Congrats. And next one, we're going to actually test it out. So how does this work? So there are some prompts and models going to generate some sequences based on that. So we can see how it behaves. Yeah, the Wi-Fi speed is not great for me. I hope it's better for you. Anyone already got their quantized models and looked at what outputs are? Yeah. So what do we see? Yeah, it should be. I mean, if my internet connection was a bit better, I would also be able to show it to you. But if you complete all that correctly, these sequences the model produced are going to be total garbage. Actually, it's going to be like not really random, but close to. I'm still at 65. Okay, I hope it will download. I'm fine. And so why do you think, what went wrong, right? Like, it's still 4 bits per parameter. And we know that 4 bits is actually enough for the model to be almost lossless. And we quantize the model, and we even ask it to continue some sequences, and it's producing rubbish. Why is that? It should work, or not? Or, yes. Yes, that's right. Also remember what I told you about, yeah. Remember what I told you about our quantization function? It's like the easiest one you can imagine. It maps values to uniform unsigned integer values. So it's like the simplest thing you can do. And also notice that as you correctly said, error accumulates. So we just quantize each row of the weight matrix independently, and it didn't do a very good job. Well, actually, to have a measure how bad our model is now you can run next several cells. This is just a helper function to be able to evaluate your model on some data set and register some perplexity value. I really hope internet is better for you than for me. Okay, I'm gonna restart the whole notebook. I hope you guys have better connection. So yeah, I invite you just to run the next cells which contain the evaluation of the model. And so we can get our perplexity value. Anyone already done that? Yeah, and so what perplexity value do you get? The 4-bit. Yeah, so our perplexity is 400 something enormous value. What does it mean? Any idea what's good perplexity is? What's a good value for large language model perplexity? 12, yeah, that's nice. And so like below 20, I say we're doing good. So yeah, model is just completely unusable, right? But as you correctly mentioned, if you just run the next cells, the model will be quantized to 8 bits. And what's perplexity on 8 bits? Could you tell me? Because it's not running for me.
Well,
Yeah, so for 8 bits, we're doing really, really good, right? So its perplexity is 12, and the model is almost unchanged. And so, all right, so we have some issue here. Like quantizing to 8 bits work, no problem. But quantizing to 4 bits break everything. And it's not our fault. It's just the method that we chose first was really, really naive and really straightforward one. So now we're approaching like the main part of the tutorial. We're gonna now do the quantization in a bit more smarter way. And we're gonna implement the GPTQ algorithm that Dan talked about before. So he gave you theoretical motivation and explanation why it works. And we're gonna implement it and see how it's working. Okay, it's still not. I'm gonna try and reload the page in hopes it works. Yes, please run. It's without GPU, please. Okay, I hope it connects. And yeah, while it's proceeding, I hope you still remember from the lecture, but let me give you a quick overview of what GPTQ's improvements are. So now we're not going to look at each row of weight matrix independently, but we are going to look at the output of this weight times input activations multiplication. And we're going to minimize the following error. So yeah, so it's a bit different notation. Multiplication happens here from like the input activations are on the left, but I hope that's the problem for anyone. And so what GPTQ algorithm asks is we are choosing the following objective. We're minimizing the error of the outputs of our layer with quantized weights versus non-quantized ones. And turns out that's a pretty good approximation to be looking at. And as I hope Dan convinced you, the Hessian of this function would be x transposed, or vice versa, like depends on your notation. And let me just go ahead and spell out the algorithm for you. So we're going to give a look at our vector values. We're going to quantize one value at a time, and not just like throughout the error, but try to modify or really modify the other weights to compensate by the error that this quantization operation introduced, right? So we try to make all weights like will work together and compensate by the errors that other introduce. And here, what we would also need is some smart inverted Hessian linear algebra. I mean, it isn't not that complicated, but I mean, it's already derived for you. So here is what our update is going to look like. So it's going to change not only the value that we've just quantized, right? It wouldn't change, but all the rest of values that are non-quantized yet, they're going to be moved somewhere just a bit to compensate by the error that was introduced. Yeah, or I can also there are more details, of course, you can read that. I mean, inverse hashing might be unstable, and we use Cholesky decomposition for that. But it's but now it's implemented for you, and what you're asked to do is to really implement the essence of the other algorithms. So this update of the other weight to compensate for the quantization error that was introduced previously. Yes, please go ahead. Yeah, so yes, exactly. So as we were doing it before, just a whole row at a time, as you can see, our 4-bit model quantized to 4 bits got absolutely broken. It's not good enough representation, right? So it just breaks the model. It's almost equivalent to random weights, essentially, right? Because perplexity went to like 400, right? So it's just essentially to have random weights. It's not good enough, so model cannot survive that perturbation. And this method we're going to implement is more careful, right? And or you can think of it is that was one, for example, zeroth order approximation, and now we try to go one order of approximation more to see how we can fix that. Essentially, we are fixing the big issue that we had with 4B model, and that requires some math machinery, right? Stellar expansion. Yeah, the hasn't been connected to the activations and the exact update formula. I mean, it's already derived for you, so don't be afraid of math. But also, if you wish, it's not a hard derivation. I'm sure you can also do it yourself if you don't trust the formula or something. Yeah, so, and I have this illustration, which I hope makes it a bit easier for you. So here the weight columns are perturbed, that the most sensitive ones with the largest Hessian values are sorted from left to right. And then we start a quantization process, moving from left to right, looking at the current column. So we quantize it, see the error that introduced, and update the right part of a matrix. So weights that are not yet quantized, that are still high precision, we update them to compensate for the error. And what's on the left, what you can see in blue, already quantized, we just leave it as is. It's already quantized weights, they are fixed. And once again, the update formula is derived for you. It's here. I mean, it looks a bit scary, but I promise you it's not. And that is essentially the update you're going to have to implement for every column. You go column by column, and for every column, it produces some update for the rest of the weights that are to the right from it. And yeah, I'm sorry, as my notebook is still not connecting. Is your Google Colab behaving all right? Because mine is not connecting. Is it working for you? Okay, I'm glad. Sorry, it's not working for me. I don't know, maybe internet connection is not that good or something. Let me try reloading the page. And I will try to How to fix that? Oh, press run all cells. Yes, without GPU is fine. Yeah, and I hope it would connect one time. So you can look at this illustration for some hint, and then you can go to the next cell, which is called GPTQ block, and implement the updates that we just talked about. And your code got here. Let me try opening the notebook one more time. Maybe Collab will collaborate with me on this one, please. Please work. Bless you. Anyway. Maybe I'm out of my quota on Collab or something. I don't know, sorry guys, it's yeah, Collab is not collaborating with me today. So how is it going with GPTQ block? I understand it looks a bit scary, like this formula right here, but it's really not. Let me try again. I just choose pure CPU. Let's try to connect. Okay, it's not working for me, the collab, but it's fine. I'm just gonna start and implementing it here anyway. I will not able to run it, but I hope you guys would. And so let's look at this formula closely. So the value that is being updated, this is a block, right? This is the whole block that goes like from orange and to this gray area to the right. So this is 2D object, right? And this is just one column. So this W and just I, as the second index, is exactly the orange column you see here, the weight matrix. And so essentially what we need to do is we need to look at these column values, look at the error, look at the error introduced by quantization, multiplied by Hessian, right? And divide over just the scalar value of inverse Hessian at position II. And then we're just gonna subtract this update from the block that we have. Let me go ahead implemented. So, oh, column weight is already there for me. I would call it quantize column weights. I will just call the function quantize on column weight. And it would require scale and 0 arguments. Okay. Then I'm gonna have to calculate the quantized value. I will Any ideas why do, oh, sorry, I think I missed bits here. Any ideas why do I need the dequantized column here too? Right, I mean, it would be stored as quantized value. Why do I dequantize it? Yeah, please go ahead. Yes, exactly. Exactly, like this subtraction operation that happens here in the nominator, it subtracts like the true full precision values minus values that are represented as quantized. But to see them in floating point, to be able to perform this subtraction, we need to dequantize them back, right? There's going to be some error introduced, and that is exactly what is captured by the formula. So that's right. All right, so I have my quantized column, I have my dequantized column. Let me write, let me update my quantized liquids. So I'm gonna put the quantized column here. I quantized it, okay. Then I'm gonna do the most important thing. I'm gonna update the weight itself with the error correction term that comes from but the essence of GPTQ algorithm. So let me go ahead and implement this. So I would need this difference between full precision weights and their presentation as quantized weights. I'm going to be subtracting. So I'm going to have my column weights. I'm going to subtract my dequantized. So I dequantized column. Okay, then I'm going to multiply it. So here you can see, I just multiply it by the Hessian. So I'm gonna, it's already provided for us, the Hessian slice. So I'm just gonna go ahead and divide by the Hessian slice. Will be fine. And I need to divide it by just one scalar value, which would be Hessian slice at index 0 and 0. Why is it 0 and 0 I'm putting here? Like in this formula, it says I and I. Why do I do 0 and 0? Or should I put something else in here? Like for this scalar value? Yes, that's diagonal, but why 0, 0 and not something else? 1, 1? Or, I mean, in the original formula, we had Hessian in this I and I, right? So why is it 0, 0 here? Or am I wrong? Sorry, once again. close, but not exactly. It's because if you look here, already our hash slice is already the path that we need for the update, right? It's already taken at indices I and from I onwards. So relative that we just need to take indices 0 and 0. Okay, but I'm asked here to return not only the updated weight, but I'm also asked to return the block error. Yeah, which looks like the column we see here. So it should be our column weights minus the quantized column. And also divided by the scalar value. Maybe I can reconnect now. My notation is not. How is it going for you? Anyone already implemented this part? Or not really, or you have no idea what's happening, or yep. Yep, so sorry. Yes, this contains integer values. You're correct. Yeah, actually, you're right. I think we need to modify it. Yes, I think we need to modify block weight. Exactly. Uh, Thank you for catching this. Yeah. So if it's running for you, have you already maybe uh, started the quantization? The next cell you can just run ahead. And oh wait, we need to do one more part before we can apply to the whole model. But how's it going with this block, with the first one, the first part? Sorry, do you have a question? Teaching assistant, can we, or maybe I can answer it? Or teaching assistant is coming, oh, sorry. Okay, yes, someone is coming to help. Thank you. finally connected to the runtime, so I can hopefully show you the values that you'll produce. Like, I hope my solution is correct. We will see when the cell runs. Fine. It started running the first cells for me, so it would take some time to go to the parts we're already at. Still. Sorry? Yeah, but maybe ask a question if you don't really, if you don't understand anything, or ask me a question why I did something that I did, or is it maybe there's a mistake somewhere? I don't know. Sorry? Ah, maybe I have a mistake also. Let's just wait until it runs and we see the tests in the next cell. Wow. Oh no, it deleted my all the stuff I already wrote before. Okay, let me just quickly because the notebook just the page updated and didn't save my previous changes, so I would have to go back and fill in some of the stuff you already did. And while I'm at it, you guys can go ahead and look at the next part of GPTQ algorithm, because we've only just implemented it for one block, but that's not all we need. And the algorithm is usually implemented in blocks. So the whole weight matrix is separated into blocks, and in each blocks, GPT, the algorithm runs independently. Why do you imagine people would do that? Why would they apply it just for blocks, but not for the whole matrix at a time? Any idea? It can help to think about the complexity of algorithm in a sense. What the shapes of all the tensors are. Like in this update formula, what are the shapes of all the tensors here? Like first we have the block, so it would be some like matrix height and like the length of number of rows that we have not quantized yet. And this values is going to be a column. As you've seen implemented, it's going to be a column. And this is going to be another block. So the answer is we run GPTQ in blocks because it uses less compute, right? We just want to save some operations, because to do it for the whole matrix at once would be too computationally expensive. We often cannot afford it. And so we look for a trade-off. So what size of blocks would we choose? So for it to have still have decent performance, but not to be extremely costly. And in practice, people usually settle for block size 64 or 128, roughly like this. Yeah, sure. Yeah, so if we're choosing smaller blocks, then we are losing some performance, right? Because to compensate for one weight error, you have just less weights to do so, right? So you have more error accumulated. But if you go too large, if your blocks are too large, it just becomes too expensive to run it. But I mean, if you wish, if you can afford it, yeah, you can do that. I mean, just in practice, people usually meet somewhere in the middle, right? So, yeah. Oh. Sorry, guys, it's not working for me again. What's sorry. You guys, please go ahead and implement the second part of GPTQ, which involves the blocks, and I will quickly fill up this stuff, which got deleted for me. Yeah. Okay, people are said leaving. Have you successfully implemented the second part of GPTQ, the block part? Where you just have to divide it by blocks, apply it block by block, and propagate the error. Any success with that? Still doing that? Okay. Yeah, sorry, guys, I guess it would take me too long to fill all the answers from the beginning. So let me just try and write down what would I do here? So we need to apply GPTQ block, which would take as inputs weights, hash and inverse, scale and 0. Okay, so it's gonna have, I'm gonna have some weights block. So this weight, so it's gonna be weight at the indices block start, and we should have block end. And we're gonna pass it through here, weight block. And we also gonna pass scale and 0. The GPT block also returns not only the weight quantized, but the error. And we're gonna update the next weight we have. So if we already proceeded with several blocks quantized by GPTQ, we have some errors stored, and we can update the next blocks, which are not quantized yet, using the error that our GPT block function is returning. So it's gonna run something, oops. Should be the error. Oh. I also need to pass the hashing slice, which would be inverse. Like this. I'm gonna pass it here. Hashing slice. And I'm gonna multiply error by the hashing slice here. So nothing does not happen here. We're just applying GPTQ block by block. And if you've done this successfully, anyone run this cell and the following one? How large value of perplexity you're getting? If you read everything correctly. No worries. You're supposed to get perplexity at around 16, which is worse than 12, of course. We're losing something, but our model is now stored using 4 times less memory. So we can afford to run it on a much smaller GPUs for inference. And that's the main gain that we're getting. So yeah, there are more helper functions here. Here's the evaluation. And if you get 16, then you've completed everything successfully. And there is the very last section. If you you want to go above and beyond to do some extra stuff on quantization about training with distillation. There's quite enough description, I think. You would be able to complete it on your own later on, or you can go find me and I'll be happy to chat about everything that's in the notebook and we did today. Yeah, I thank teacher assistant very much. And I thank all of you for coming. And I hope now, yeah, you have a better understanding of GPTQ and you now can say that you've touched quantized weights with your hands. Yeah, thank you very much.